The game of checkers, or drafts, operates within a vast 32-node discrete phase space matrix. A phase space geometrically maps every possible system state to a unique mathematical point. For checkers, this landscape contains approximately 10 to the 20th positional states. Navigating this immense matrix requires massive computational architecture. Beginning in 1989, researchers at the University of Alberta developed the Chinook project, an advanced artificial intelligence designed specifically to map and conquer this exact 32-node lattice. After nearly 2 decades of processing, the Chinook team achieved their goal in 2007. They mathematically solved checkers, proving that perfect play from both sides invariably results in a draw. Chinook achieved this perfection by building an absolute algorithmic safety net. The engine relies on a flawless endgame database containing 39 trillion configurations. This database provides absolute game-theoretic certainty, an instant win, loss, or draw verdict for any board state containing 8 or fewer pieces. Within an infinite computational horizon, the Chinook algorithm exists as an invincible, mathematically closed system. Under these parameters, it is a machine incapable of defeat. But the absolute invincibility of a state machine only holds when it has access to its full computational resources. In a specific documented engagement, a human operator intentionally restricted Chinook's processing parameters. Under these constraints, the invincible machine failed. The encounter resulted in a total mathematical and topological surrender by the artificial intelligence within exactly 43 moves. The structural pressure applied to the algorithmic entity triggered hard-coded developer artifacts within the user interface. The system began emitting emotive surrender messages, outputting the text, "Chinook's analysis. Oh no. My opponent is winning." Geometric phase trapping allows a human operator to induce this structural collapse by exploiting the inherent blindness of the machine's evaluation systems. This encounter exposed a specific structural flaw in how bounded algorithms perceive reality. To understand the trap, we must examine the architecture of Chinook's mind. It does not evaluate the board through spatial intuition. It relies on brute force linear minimax depth searches. Minimax is a decision rule used to minimize the maximum possible loss in a worst-case scenario. The operator exploited a vulnerability by applying a bounded horizon. This artificial depth limit severed the state machine's access to its 39 trillion state endgame database. Below this boundary, the algorithm is blind to game-theoretic certainty. It is forced to rely on linear heuristic evaluation functions to assign scalar weights to the board topology. A heuristic function is a mathematical shortcut used to estimate a value when the true outcome is too complex to calculate. This constraint isolates the artificial intelligence. Because it navigates the phase space using linear depth searches, it evaluates disconnected nodal states. It lacks the capacity to perceive the macroscopic, continuous topology of the board as a single unified manifold. A human operator, however, possesses spatial awareness. This allows them to identify continuous phase spaces inside discrete structures and recognize the board's overarching geometry. Restricting the machine's event horizon breaks its ability to verify the future. It leaves the linear evaluation system susceptible to direct manipulation. The breakdown occurs at move 32 of the engagement. At this point, the conflict transitions from numerical calculation into the realm of pure geometric topology. On move 33, the human operator executes a tempo maneuver. A crowned king is shuffled backward, moving from position 15 to position 10.
The algorithm advances, and on move 34, the trap shuts. The human operator returns the king to its original square at position 15. This chart shows the AI's internal heuristic evaluation trajectory during this sequence. We can see the mathematical impact of the move 33 phase shift as the machine's internal scoring begins a sudden descent. The human maneuver creates a temporal vacuum. This is a reversible phase shift that forces a null state in the operator's spatial advancement without weakening their defense. The state machine is bound by a rigid requirement to increment its ply clock forward. A ply clock is a counter for each individual turn taken by a player. By passing the tempo, the human forces the algorithm to step forward into a geometric trap. Looking down its bounded future decision tree, the AI calculates that every single available branch returns a strictly negative scalar weight. The graph tracks these scores plummeting as the machine realizes its position is worsening. Recognizing geometric doom, the algorithm discards a piece in desperation on move 34. This sacrifice grants a permanent material advantage, ensuring a total systemic collapse. This state is called Algorithmic Zugzwang. It is a specific spatial configuration where every legal move actively ruins the entity's position. The human operator weaponized the AI's own forward momentum. They compressed the machine's phase space volume to 0 without altering the macroscopic board state. This checkers exploit mirrors a persistent schism in theoretical physics, the gap between continuous reality and discrete systems. Physics struggles to reconcile general relativity, which models gravity as a smooth manifold, with quantum field theory, which views matter as discrete excitations. This conflict raises a difficult question. How do fundamental mathematical invariants, like geometric dominance, survive when transported across different dimensional boundaries? Standard analytical solvers frequently treat these transitions as computational failures or paradoxes. The theory of infinity introduces the mathematical worm to carry invariant records across disparate topologies. The head ingests the payload, like the human's positional advantage. The body navigates the not-infinity boundary using symmetries. The tail re-emits the payload, applying a beta lift to preserve data. The mathematical worm is a rigorous protocol designed to ensure the conservation of modality. It allows stable mathematical laws to persist across disparate topological frames that would otherwise be incompatible. Within this framework, the checkers maneuver is classified as an exploratory worm. The human operator successfully transported a geometric invariant across the 32-node discrete lattice. The temporal vacuum altered the AI's internal evaluation modality, while the deeper macroscopic positional reality remained perfectly invariant. The human successfully carried the fact of their win through the machine's attempt to calculate it away. This mechanism applies to advanced geometry. Here, a Euclidean partition is compared to a hyperbolic partition. An exact worm transports the Euclidean modality into a four-dimensional Minkowski spacetime. Despite the violent boundary shift, the exact unit volume and global integrity are preserved. The continuous calculus of the hyperbolic worm and the discrete lattice of the checkers exploit are two sides of the same coin. Both demonstrate how to move an unchanging truth through a shifting mathematical environment. Whether evaluating the infinite continuity of complex calculus or navigating bounded logic gates, macroscopic pattern recognition identifies truths that linear calculation cannot reach. In any system, the laws of geometric topology reign absolute.